Hi everyone, this is pre-class video on module 5 power system stability. In this video I will be explaining the derivation of swing equation, multi-machine system analysis and machines swinging coherently. Concepts I will be explaining in this video. Myself Dr. M. J. Chandrasekhar, Associate Professor, Department of EEE, SAB Institute of Technology. In the first session, I explained the introduction to power system stability, classification of power system stability, rotor angle stability, voltage stability, frequency stability. Along with that, I explained the dynamics of synchronous machine. So, let us consider the swing equation. Swing equation, it describes the variation of rotor angle with respect to the power output. See here, let us consider a synchronous generator or a synchronous motor. See here, we have a generator. If you consider the input is mechanical power, that is Pm is the mechanical power input, and the electrical power output you will be getting by converting mechanical power to electrical power. That is the function of the generator. And in the motor side, we are giving electrical input and we are getting the mechanical power output, and the torque and the angular speed is mentioned here. So, in this let us take the electrical torque output Te is equal to Ti. Here we have neglected any retarding torque due to rotational losses. Therefore, we will get Te is equal to Ti. So, Te into Ws is equal to Ti into Ws. So, this can be written as Te Ws minus Ti Ws is equal to 0, that is Pi minus P. When we change the load or the fault happens, then the input power, that is Pi, the input power Pi is not equal to P. Therefore, left hand side of the equation is not 0, and an accelerating torque comes into play, that is the electrical power and this. So, power is equal to torque into, so that is torque is equal to power divided by angular velocity. This formula we know. So, this is not equal to 0 when there is any disturbance. If Pa is the accelerating power, then the Pi minus Pe is m into d square theta e over dt square plus d into theta e by dt is equal to Pa, that is accelerating power. The difference between the input power and the output power is the accelerating power, that can be written as m into d square theta over dt square. As we know that torque is given by inertia constant into alpha. So, alpha is acceleration, that is d square theta over dt square. Ta is I into d square theta over dt square, where I is the moment of inertia of the rotor, in kg meter square, and alpha is the angular acceleration in radians per second square, and theta is the angular displacement in radians. So, here m I told you m is nothing but the moment of inertia, and d is the damping coefficient, and theta is the electrical angular position of the rotor. So, here it is more convenient to measure the angular position of the rotor with respect to the synchronously rotating frame of the reference. So, therefore, you can write delta is equal to theta minus Ws into T. So, we can write d square theta e over dt square is equal to d square theta d square delta over dt square, where delta is the power angle of the synchronous machine. So, if you neglect the d is equal to 0, damping coefficients d is equal to 0, substitute this in the previous equation, we will get m d square delta over dt square is equal to Pi minus Pe. So, we know that m is equal to Gh by pi f into d square delta over dt square is equal to Pi minus Pe. So, this can be written as m in per unit is d square delta over dt square is equal to Pi minus Pe. This is per unit. Here m in per unit is h divided by pi f. So, this if you substitute in the previous equation, you get h divided by pi f is d square delta over dt square is equal to Pi minus Pe. We are expressing this in per unit. So, the above equation, this equation is called the swing equation. The swing equation. This equation describes the rotor dynamics for a synchronous machine. Damping here we have considered by dynamically stability study. Next, we will see the multi-machine system. So, in a multi-machine system, a common base must be selected among the different machines. So, the common base here is G. G machine, let it be the machine rating in base, and G system is the system base. So, the equation what we have in the previous slide, this equation is the swing equation. Let us write here. So, that can be written as G machine divided by G system will give in per unit to H machine divided by pi f d square delta over dt square is equal to Ps minus Pe, or Ps is the mechanical input or the shaft power input or input to the motor electrical power output, into G machine divided by G system. So, this can be written as H system, m is equal to Gh by pi f. With that we can write this pi f d square delta over dt square is equal to Pi minus P. So, this is written in per unit on system base. So, here we have considered H system. H system is G machine divided by G system into H machine. This is called machine inertia constant, inertia constant in system base, in system base. This is machine. Now, we will see the next concept, that is machines swinging coherently. That means, if multiple generators are connected in parallel, if there is any disturbance in the terminals of the generators connected in parallel, all the generators gets affected due to the disturbance in any one of the terminal of the generator, because all the synchronous machines are connected together. So, all will rise or accelerate or decelerate their rotor speeds coherently, means together. Let us consider the swing equations of the two machines on the common base. So, H by pi f, H1 is the first machine inertia constant, d square delta by dt square. For first machine I will mark 1 suffix, pi minus pe, pi minus pe, I will write suffix as 1 to indicate the swing equation of the first machine, and second machine similarly we can write 2 d square delta 2 over dt square is equal to pi minus p 2. So, since the machine's rotors swing in unison, so because these two motors are swing unison, the deflection in the rotor angle will be same for both the machines. Deflection in the rotor speed remains same because they are connected in unison. So, adding these 1 and 2, so adding equations 1 and 2 and substituting equation 3, we get so here Pi is the input power, total power input is Pi1 plus Pi2. So, Pe is the electrical power output, this is the sum of the electrical power of the two machines, and H equivalent, inertia constant of the two machines, is added together. So, equivalent inertia constant H equivalent can be expressed as this G1 machine divided by G system into H1 machine plus G2 machine divided by G system into H2 machine. So, this is how we can analyze the machines swinging together. So, with this I will be ending this video.